What actually is electric current? People say things like current flows through a wire, this charger outputs 2 amps, too much current can burn a circuit. But what is current physically? What is actually moving inside the wire? And why does electricity sometimes behave almost instantly, even though the particles inside move incredibly slow? Today we are going to break current down visually and simply. No complicated math, just the real idea behind what electric current actually is. The easiest way to understand current is to imagine water flowing through a pipe. Voltage is like pressure. Current is like the amount of water flowing. A small trickle of water means low current. A huge rushing stream means high current. Electric current works similarly, except instead of water molecules moving through a pipe, we have tiny charged particles moving through a wire. Inside metal wires, there are billions upon billions of tiny particles called electrons. Electrons carry negative electric charge, and metals like copper are special, because some of their electrons can move free. Normally, these electrons move randomly in all directions. There is motion everywhere, but no overall flow. So, even though electrons are constantly moving, there is no electric current yet. It's like a crowded room where everybody walks randomly. People move, but nobody moves together in one direction. Now let's connect a battery. The battery creates an electric field inside the wire. That electric field pushes electrons, and suddenly, those randomly moving electrons begin drifting in one general direction. That organized movement of electric charge is electric current. That's the key idea. Current is simply the flow of electric charge. In metal wires, that charge is usually carried by electrons. Current doesn't describe how fast a single electron moves. Instead, current describes how much charge passes through a point every second. If more electrons pass through the wire each second, the current is higher. If less electrons pass through, the current is lower. Current is measured in amps. 1 amp means a certain amount of electric charge moves past a point every second. So when your phone charge says 2 amps, it means charge is flowing through the circuit at a certain rate. Here's the part that surprises most people. The actual electrons inside a wire move very slow, really slow, often only millimeters per second, in some cases slower than a snail. So wait, if electrons move so slow, why does the light turn on almost instantly when you click a switch? Great question. Imagine a long tube packed full of balls. Push one ball into the tube, and the ball pops out the other side almost immediately. Even so, each individual ball barely moves very far. Electricity behaves similarly. The wire is already filled with electrons. When the battery pushes electrons at one end, the push gets transmitted through the electric field extremely quickly, almost at the speed of light. So the energy moves fast, even though individual electrons drift slow. This is important. The electrons themselves are not tiny bullets shooting from the battery to the light bulb at light speed. Instead, energy is transferred through the electric field inside the circuit. The electrons mostly drift locally, but together, they transfer energy through the system incredibly fast. That energy powers your lights, your phone, your computer, and basically every electronic device around you. There are also different types of current. Direct current or DC flows mostly in one direction. Batteries produce DC power. Alternating current or AC constantly reverses direction. That's the type used in power outlets in homes. In AC electricity, electrons don't travel huge distance through the wire. Instead, they mostly move back and forth very fast. But even that back and forth motion can still transfer energy efficiently. Current also depends on resistance. Resistance is anything that makes it harder for electrons to move. Thin wires have more resistance. Certain materials resist electrons' flow more strongly. And components like resistors are specifically designed to limit current. You can think of resistance like narrowing a water pipe. The harder it is for change to move, the less current flows. There is a famous rule in electricity called Ohm's law. It basically says current increases when voltage increases and current decreases when resistance increases. More electrical push means more flow. More resistance means less flow. Tiny currents power LEDs and sensors. Larger currents run laptops and gaming PCs. Massive currents power electric cars, factories, and entire cities. The exact same principle works anywhere. Moving electric charge transfers energy, whether it's a tiny smartwatch or a big power station. So let's simplify everything into one idea. Voltage is a push, current is a flow of electric charge. Resistance makes the flow harder. Inside wires, electrons move really slow, but the electrical energy moves through the system incredibly fast. And that invisible movement of charge is what powers the modern world, electric current, one of the most important flows in human history.